Because at this point, we do not know how much is the cost of building the heap. Okay? Yeah. So what do we need to do? We need to estimate the cost of building a heap. Yeah. So actually, we should say building a max heap. Okay? Yeah. All right. We know if it is big O of n squared, yeah, big O, it's better we use big theta. Okay, all right. If it's a big theta of n squared, then we should stop immediately, right? Because it does not make sense to do the remaining part. Already, this cost is so high, that means useless. This whole thing, whole method is useless. Okay? Yeah. Then stop. Okay? Yeah. Too bad. Yeah. But if it is big theta of n log n, n log n, it is, you can see, it is already the average case, right? So if this one, actually, we feel not very good. Not very good. Yeah. So the value of this method, is not that big. Yeah. Yeah, because you already spend this much resource on just building a heap. Yeah. Then your gain, because you need to continue, after that you need to continue to do the heap sort. So the whole thing, it looks like not very promising. Yeah. So we get a feeling like that. But if it is big theta of n, okay, yeah, then it's very encouraging. Okay, yeah, big theta of n. Yeah. Acceptable, yeah, because our bottom line is, so this is the bottom line. Bottom line. Yeah. Now, still, we have a lot of room, right? Yeah. So, this means we can proceed. Yeah, it's encouraging. Yeah, we can proceed. Yeah. So that's the current situation. Yeah, before we start, so we want to see, yeah. All right. So but to do this estimation, it's not easy. We need to do a lot of work. Yeah. All right. So the first thing, we need to do the counting. Yeah. Number of leaves in a heap. Yeah. So do you still remember when you learn the data structure? Not the data structure, the discrete math. Yeah. I don't know if in the discrete math, if you learn this concept, the leaves of a tree. You have many nodes. Yeah. Yeah. Some of the nodes we call the leaves. From the names you can guess the meaning of the leaves, right? So let me describe the leaves. In this tree, yeah, some of the nodes, they do not have any child. No child for these special nodes. Leaves, yeah, tree, so you grow trees, so leaves, yeah. The leaves appear at the end of the, right, the boundary, near the boundary, so no further child nodes. Yeah, that's the leaves. Yeah, so nodes without children. That's the definition for the leaf nodes. Yeah, all right. So here you can see these 3 nodes at the bottom and the 2 nodes in the higher level. Yeah, total these 5 leaves. Yeah, all right. Then the question. Let me give you the question. Given a tree, given a heap, yeah, because here our tree is not arbitrary binary tree, right? Yeah, our heap is not an arbitrary binary tree. It's we call it a near complete binary tree, right? So that's our tree, near complete binary tree. The question, given a near complete binary tree with n nodes, so you're only given with n nodes. The n number, I'll give it to you. Yeah. My first question, can you tell me how many leaves can you find in this heap? How many leaves? Yeah. N. Yeah. If n, let me say 1,245, for example. Can you tell me how many leaves in this heap? Yeah. The question, first one. So we need to find the formula to calculate the number of leaves. Yeah. Here, let's do the calculation. Yeah. All right. Parent-child relationship. Yeah. Yeah. All right. When our parent node occupies A of I location in the array, then the left child, so here we only look at the left child, not right child. Yeah. Left child here is better than the right child. Do you know why? Yeah, Matthew? Why left child is better than right child when we discuss the relationship?
Because some nodes that have children will have a left child and not a right child.
That's correct. That's correct. Yeah. Because when we consider the child nodes of one parent node, it has left child first, then right child, right? Right child after left child. So there is a situation, some node may only have a left child node but no right child node. For that reason, availability. So the availability of left child node is higher, better than the availability of the right child. Yeah. All right. Then, if there is a left child, it must occupy that A of 2i, that location. Now, can you tell me based on this? So this is a fact. So we examine this fact or property. Yeah, you call. Yeah. Can you tell me under what situation a node does not have any child node? I want to ask you, under what condition a node does not have any child node? Can you see that from that relationship? Yeah. 2i, okay? 2i, think about this 2i. For what condition on this 2i? You do not have it. You do not have it. This parent node does not have any child node. When this 2i is out of bound, right? Out of bound. Yeah. Remember array locations. Yeah. Locations in the array. Okay? Yeah. Our current array. Current array. Locations we use from 1 through n, right? We skip that 0 location. Zero location, we cannot do anything. Okay? Yeah. So location number from 1 through n. That's the range for the locations. But how about when this I out of the range? When you double this I, you get out of the range. Out of this range. Then, no child, right? Yeah. So that's simple. If it's out of range, if 2i is out of range, that means this I node does not have any child. That's simple. In other words, for an I node to have a child, 2i must be in the range. Yeah. 2i must be in the range. Yeah. So now you have an inequality to describe. In order to count the number of leaves, you need to have a constraint. Yeah. Constraint. Yeah. All right. Yeah. Out of the bound, out of the range. Yeah. Meaning of no child. Yeah. All right. Yeah. Yeah. Meaning of no child. Yeah. Because why? First, I must be in the range, right? If it's a node, it must be in the range. I less than equal to n. That means I is in the range. Yeah. But 2i is out of the range. 2i must be strictly greater than n. No child. Then, meaning no child, does it mean a leaf node? This gives us the condition for a leaf node. So you can see if an I satisfies this inequality, that means A of I, that element must be a leaf node. That's simple. Okay, yeah, that's simple. Now, let us solve this inequality to find the range for I. We need to see what is the range for I. Range for I, that means we need to find the lower bound for this I and the upper bound for this I. So then all the numbers between this lower bound and the upper bound must correspond to a leaf node. Yeah. All right, so let's solve the inequality. It's pretty simple, right? Yeah, all right. Inequality. N over 2 must be strictly than I. Yeah. N over 2 must be strictly than I. Yeah, strictly than I. Now, the question I want to ask you, what is the best lower bound? We want to find the lower bound. The best lower bound for I. Best lower bound for I. Strictly less than n over 2. What is the best lower bound? Can you see it? You can use floor function, ceiling function. Yeah. But the main difficulty we need to handle here is this strictly less sign. Yeah. N over 2 is strictly less than I. We want to see the lower bound of I. What's that? What is the smallest possible I value that is strictly greater than n over 2? Considering both cases, even n and odd n. Yeah. All right. So when n is even, so here, let's do this way. When n is even, what is that number? N over 2 is an integer. I is strictly than n over 2. What's that? N over 2 plus 1, right? You cannot choose n over 2 because n over 2 is not strictly greater than n over 2. It must be n over 2 plus 1 when n is even. Then when n is odd, what is that number? N is odd. Yeah. Integer. Yeah. n over 2 greater than that. Yeah. What is that? Yeah. N over 2. Yeah. Strictly, yeah. Yeah. Is it n over 2 seeding function? No. No. Strictly the n over 2, but it's an integer. Okay? All right. How do you get an expression combining these two? Yeah. We want to find one expression combining these two. Yeah. Because we do not want to write twice, right? We want to write a unified formula covering both cases. Yeah, that's what we want to do. We want to find a uniform formula covering both cases. All right. Floor function of n over 2 plus 1. Floor function plus 1. Floor function plus 1. Covering both cases. You see? When n is even, the same as the first expression. When n is odd, the same as the second expression. Yeah, but we want one expression, not two. A unified expression. Okay, yeah. All right, that's the first step. The question, that's lower bound. How about upper bound? Upper bound easy, right? N is upper bound. From the given constraint, yeah, that constraint we just discovered. Yeah. Upper bound, we have the upper bound immediately. All right. Then the whole range, this is the best range we find for the leaf nodes. Right. Now I ask you the question. You need to do the counting. Based on this inequality, you tell me how many I numbers fall into this range. You need to give me the counting. How many I numbers fall into this range? Any idea how to calculate that? Is it upper bound minus lower bound? Do you upper bound minus lower bound? But you need to think carefully. Upper bound minus lower bound. Do you minus too much, right? Do you minus too much? Upper bound minus lower bound. Answer is n minus floor function of n over 2. N minus floor function of over 2. Can you see that? Can you see that the answer? Yeah. All right. Let me ask you a simple question. All right. In order to help you understand how to do the counting in this situation, yeah, let me ask you a question. How many numbers, how many integers between 23 and 47? How many integers in this range? Tell me. You count. Count the number. Count the number. Anyone can give me that number?
24.
Matthew?
Since it's inclusive, it's at 25.
Good. Inclusive. 24. You use 47 minus 23. You minus one more. Okay? Because when you minus 23, you exclude that 23, right? But we need to include it. So you need to add one back. Okay? So you usually, when you do subtraction, you should use the upper bound to minus 1 before 23. Okay? Because you don't want to exclude the 23. One number right before this 23, you should minus 22. Okay? 47 minus 22. Yeah. Here, we do the same thing. When we need to count the number in this range, we use the upper bound to minus the number, just the one right before this number, that is this one, right? Seeding function, floor function of n over 2, the plus 1, we do not want to remove that. lower bound. We want to include that lower bound. Okay, that's why you have n minus floor function of n over 2. Okay, all right. That's the first step. We have formula. Then, if I ask you the question, given let's say a heap, okay? Given a heap with 1,247 nodes, now you can use this formula to tell me the number of leaves immediately, right? Yeah. All right. Yeah. Then, another thing. Yeah. So this formula, we have another expression to write this formula. Yeah. That is, it equals the seeding function of n over 2. Yeah. Equals the seeding function n over 2. Yeah. All right. How do you see it? Yeah. So in our appendix of our textbook on page 477, in the appendix, this formula is given. Yeah. The formula is given. Okay? We can apply this formula. But you may ask me how to prove it, right? If you ask me how to prove it, then it's easy. We do discussion on two cases. When n is even, can you verify this formula when n is even? Easy, right? Yeah. Then, second case, when n is odd, can you verify this formula? If you verify both cases, you prove it. Yeah. Yeah. All right, so here, we can use this formula. Yeah. So here, we have two expressions. This first expression, second expression. Sometimes we have freedom to choose which one to use. Yeah. Sometimes the first formula is a little better. Sometimes the second formula is a little better. Yeah. All right. Yeah, so we complete. Then, we go to next level. So we find the number of leaves, but how about one level higher? Yeah. One level higher than the leaves. How many nodes in that next level? Yeah. Leaf level. Yeah, we know. Yeah, leaf level. We treat leaf level as our ground level. Yeah, it's ground. Okay. Yeah. So the tree upside down. Okay. The root in the sky. Okay. Upside down. Leaves at the bottom. Okay. But leaves, we treat the leaf level as our ground level. How about that? Then one level higher than the leaf level. How many nodes? Yeah, because here we need that concept. We need that concept. Yeah, all right. Number of internal nodes with height 1. So here, two concepts. First, internal node concept. Second, height concept. Height concept. Okay, all right, let me explain. Internal node, then when you have internal node, you have external nodes. Yeah, two types of node. A given tree has these two types of node, internal node and external nodes. External nodes, the same as the leaf node. Leaf external, okay? Leaf, yeah. Outside, boundary, external, yeah. Leaf nodes, externals. Just a different name for the leaf nodes, external node. Then, for the nodes other than the leaf nodes, that's internal nodes. Yeah, because each internal must have at least one child. At least one child. Yeah, that's the internal nodes. Yeah. All right. Yeah, from this example, you can see, these are the internal nodes. Okay, internal nodes with height 1. Here we need to define this height concept. Height concept. That's why I continue to use that ground level, right? Because we treat leaf level is ground level. Ground level means the height equals 0. H equals 0. That's the ground level. Okay? That's the leaf level. They are the ground. Yeah. Height. We count the height starting from the ground. Okay? So the ground level height is 0. Then, next higher level height 1. Now you know these three red circle nodes, they have height 1. Because from this node, after one edge, look at that, one edge, you reach the ground level. You reach the height level. Okay, but you need to use one edge to go to the next level. Yeah, we count the number of edges. Okay, yeah, so the height 1. All right, yeah, because later when we talk about the number of leaves with height 1, yeah, when I gave these questions before, many students, they used the wrong understanding. Yeah, I will talk about that. After I finish this topic, then I will talk about that common error. Yeah. So, when I did a grading before. Yeah. Yeah. All right. So let's do the counting. Yeah. So here, the similar question as the previous slide. Yeah. Given a heap with n nodes, I want to ask you this question. How many internal nodes with height 1? Yeah. How many internal nodes with height? You need to do the counting. Yeah. Here we need to do the similar counting, right? We just did. We have the experience counting number of leaves. Can we apply the similar method to count the number of internal nodes with height 1? Yeah. Because it has a property. When you look at its left child, now we still look at the left child. When you look at its left child, its left child must be a leaf, right? Yeah. The height 1 internal node, every height 1 internal node, it has this property. Its left child must be a leaf. That simple. Yeah. How to get its left child? Double index, right? Double the I. So 2i must fall in the range for the leaf. 2i must fall into the range of leaves. Okay? Yeah. For the leaves. Yeah. All right? And then we know the range for the leaves, right? Yeah, we have inequality for the range for the leaves. Yeah. So that's simple. Yeah. Let's do it. Yeah. All right. First, internal nodes, external nodes. Total nodes, we have n nodes. All right. And number of leaves, we have the formula. Yeah. This many number of leaves. Can you tell me how many internal nodes? The complementary part, right? Yeah. Because other than external nodes, leaves, the remaining all internal nodes. So the complementary part, that's the internal nodes. Yeah. The number flow function of n over 2. Okay? Yeah. All right. Then the number of nodes with height 1. That's what we're doing at this point. Yeah. All right. Their children are leaves, yeah, especially the left child. Evan, want to say something? Oh, you got the answer?
I think so.
Oh, good, very good. All right, we will get there quickly. Yeah. So then I may ask you some question. Yeah. Then, because 2i must fall into the range. This is the range for the leaves, right? Exactly. We copy the range. But when we copy the range, we should put a 2i in this inequality, not I, right? Yeah. Question. Can we find the range for I? Because our goal, we need to find the range for I. Okay? All right. Yeah. So let's do division by 2 operation. We do division by 2. Yeah. But when you do division by 2, you need to consider your upper bound and lower bound must be integer expressions. Yeah. It cannot be non-integer expressions. Okay, your upper bound. And this is a simple upper bound. You can see immediately, right? Divided by 2, but divided may not be integer, you do flow function, make it integer. Yeah. But the lower bound, can you see the lower bound is like that? It's not easy to see, right? Yeah, Kirill, is it easy to see the lower bound? Not quite, right? Not quite. Not quite, okay? Yeah, yeah, yeah. But because there is one more step here, yeah. So before the step, there is another step. Before the step, there is another step, okay? All right. Yeah. So divided by 2, divided by 2. All right, so let's do this. When we divide it by 2, plus 1 divided by 2. Yeah. This number may not be an integer, right? Yeah, we know. Sometimes it's an integer, sometimes it's not an integer. Okay? Yeah. Sometimes integer, sometimes not an integer. Yeah. All right. When it is not an integer, we need to take the ceiling function, right? Yeah. Ceiling function. Yeah. So the question is, this expression should be the lower bound? Yeah. Because if an integer, when we take ceiling function, the same number, right? If it's a non-integer, we take ceiling function, then that's the one we need for the lower bound. Both cases, that expression should be the lower bound we need, right? Yeah. Yeah, it's correct. Yeah. But that expression, can you see that expression is the same as this one? Because that expression, although it's correct, but it's not very simple, right? Relatively complicated. Yeah. Can we simplify it a little more to get a slightly simpler version of the same formula? Yeah. Yeah. Here we need to prove it. Yeah. To do that, you need to prove it, right? Yeah. Yeah. To do that, okay. All right. So the ceiling function like this. This is the ceiling function. Okay. I just split. You know, I write it in a split way. Okay. All right. Then we take ceiling function. Yeah. All right. Now we need to prove this equality or identity. The question, how to prove it? How to prove it? Yeah. We did one before, remember? Let's recall. We did one, n over 2 plus n over 2 equals n. Yeah. We use two cases to do the verification. N is even, N is odd. Yeah. Here, can we use certain number of cases to do verification? Yeah. Yeah. But here, two cases is not enough. If you only consider even odd case, not enough. Yeah. Here, we need to use 4 cases. Yeah. And mod 4. You need to do the modular operation. N mod 4. When you do n modulo 4, how many cases you need to consider with the remainder cases? Remainder 0, 1, 2, 3. So this time you need to consider, do verification for the 4 cases. If you use the expression, n expression for 4 cases, the first expression, n is 4k. Remainder 0. Second case, 4k plus 1. Third case, 4k plus 2. Fourth case, 4k plus 3. If you verify this equality it holds for all these 4 cases, you complete the proof. Okay? So here I just tell you how to prove the equality. What ceiling function, floor function, when you need to do discussion. Okay? Yeah. All right. Yeah. So here I do not do it. Yeah. The result, it is correct after verification. All right. Then we need to count the number of i's in this range using our counting method before. Upper bound, this number, minus not the lower bound directly, but the one number right before this lower bound. So we do not include that plus 1. So you get this expression. That is the number of internal nodes with height 1. Okay, with height 1. That's the formula. Yeah, right. And in this one, this formula is less than or equal to the ceiling function of n over 2 squared. Less than or equal to. Okay? This time it's not equal. Yeah. Not equal. It's different from our previous case. Our previous case, n minus the floor function of n over 2 equals ceiling function of n over 2. But in this case, not less than or equal to. That's the important change. Yeah. Why not equal? Because you verify these 4 cases. 4k, 4k plus 1, 4k plus 4. Some of the cases they are equal, some of the cases they are different. That's why not equal, less than equal to. Yeah. Yeah. And inequality, sometimes it's okay. We can use this inequality because this expression simpler than that expression. Okay? The difference is very small. Yeah. Yeah. There is a small difference. Yeah. The difference. Yeah. The difference is 1, right? Both integers. Yeah. Yeah. So for some of the 4 cases, they have difference 1. Yeah. For some of the 2 cases, they are the same. Yeah. But only one difference. Sometimes, we can accept that one difference, right? It's not a big deal. Yeah. Yeah. All right. So that's the height 1. We complete the height 1 formula. Yeah. But when you calculate, you need to use that exact formula. Do not use this approximate formula. Yeah. But approximate, you have one difference. You may have that one difference. Wrong answer. But this is exact number. That's a, slightly larger number. Yeah. Slightly larger number. Yeah. All right? Yeah. All right. Number of internal nodes with any height this time. Yeah. Any height. Yeah. Height 1. A special case. But now we need to do the counting. Any height. Yeah. Yeah. So now we can get that. Generalize the previous result. Yeah, generalize. Yeah. This time we have a lot of experience. Yeah. So we know how to do it. Yeah. The number of leaves, this many. Yeah. All right. Height 0. Yeah, that's. Yeah. Number of nodes with height 1. Our formula becomes this formula, but that's. Yeah. So this is the counting. Okay. The number of nodes. That's the counting number. That number. Can you go another level? Yeah, because based on this one, yeah, the information, the structure of the formula, can you go one level higher? Height 2. Yeah. We want to count the number of internals with height 2. One step. Yeah. Higher. Okay. Yeah. Number of nodes with height h. Yeah. Because look at the power of 2. Okay. This one 2 to the first, okay? This one 2 to the first, and 2 to the second, all right? Yeah. But 2 to the first, this number corresponds to the high number, right? Corresponds to the high number. Then the exponent number here, 1 higher than the high number. This 2 number, 1 higher than the high number. Yeah. Based on this observation, can we write out the number of nodes with height h immediately? Yeah, based on that observation, do analogy, right? We do our deduction by analogy. Okay, all right, yeah. How about this? Yeah, all right, yeah. But this one here, you see, yeah, we should use the height number, okay? Yeah, n over 2, power of 2. Exponent number, we should use the high number based on here. Okay, high number. Then this side, we should use the high number plus 1. High number. Okay, yeah. That formula. Okay, yeah. If you want to see why it's true, you double it, right? double it, it's the lower level. Yeah. Here, this thinking, when you do the thinking in this way, one important thinking you need to use. Yeah. I mentioned before in our module 3, when we studied the Fibonacci numbers, yeah, I introduced a powerful mathematical tool. Yeah. Here, you need to know that tool when you do the thinking. It's called a mathematical induction. Okay? And that powerful tool we call it mathematical induction. Okay? Yeah. Yeah. We need to use that thinking, all right? We start from h equals 1. Then we go next level higher. Then when we double the index 2i, then 2i should fall into this range, right? Then we divide it by 2, just like what we did previous round. Yeah. Then we simplify, we prove, Then go to another level, okay? Level by level, but when we cannot do all the levels, right? So if we cannot do all the level, we use mathematical induction to study 2 adjacent level. How about that? Yeah, relationship between 2 adjacent level, right? So then we can get it. Yeah, yeah. So here I skip the details, yeah, because I want to save time. Yeah, I'll just tell you, when you want to do the rigorous thinking, you need to do this way. Okay, that's the rigorous thinking. Yeah. All right. Now here, this is the result. Okay, the range for the height h nodes. Height h nodes. Okay, all right. Then when we do the counting, now we do the counting. Upper bound minus the number 1 smaller than the lower bound. All right, this number 1 smaller than the lower bound. Yeah. That's our counting number. Okay, yeah. All right. Then we get all our answers. Yeah. So this time, yeah, now I want to explain. Yeah, so one common question. Yeah. So many students did, before. Yeah. All right. Those students, they didn't follow the lecture closely. Yeah. Especially those online students. They didn't watch the videos. Many online students, they didn't watch the videos. Because that's the only way they can learn the lectures, right? Learn the materials. But, yeah, based on my YouTube hits, number of hits, I can see, many students, they didn't watch the videos, okay? Yeah. Then, they work on the homework questions without watching the videos. Many students did that. All right. Then, when they see the concept, they just guess. They guess, okay? I ask them, okay? I ask questions like this. Given certain number of nodes, okay, 100, 2,000, some concrete number. Okay, I ask them how many nodes with height 2, for example. For you learn the lecture, how many nodes with height 2? Yeah, you use this formula, right? H equals 2. You plug in, you do the calculation. Yeah, but those students, they don't know these formulas. Okay. So first, they want to calculate by themselves. Then, first they need to understand, what do you mean height 2 nodes, right? Internal, they don't know what's the meaning of height. So they interpret in this way. Okay, let me tell you, that's that way. When our height concept, we come from the ground level, right? Above. Ground level, starting ground above the height. They come from root. That the starting point is the root. Okay? All right. So they do this. Starting from root. That 2 nodes below. 2 nodes. Okay? Yeah. And they treat this as the height. Height 2. All right? So then they calculate. So this number, they give me 4. This number is the height 2 number. So many students did that way. They give me this number, all right? Yeah. So this concept we do not call height, okay? There is another concept. This concept we call the depth. It's not a height, okay? Depth. Yeah. There is a concept for that. Where we come from root, yeah, it's depth, okay? Yeah. So our reference point is root. Yeah. So if you treat that root level as the 0 level, depth 0, root depth 0. So then you go to the underground, right? Yeah. Underground. So it's depth. Yeah. Under the 0 level, underground level. Yeah? Yeah. Because this is the depth d equals 0 level, okay? Yeah. Then under the ground, the depth, yeah. Height, above the 0 level, okay? Higher height and the depth, yeah. Two concepts. Yeah. All right, so that's one common mistake. Yeah. All right. Next, we need to estimate the cost, the building cost. Yeah. B.2, the building cost of the heap. Now with the inequality, the estimation is pretty straightforward. Yeah. All right, so let's do it. Yeah. Combine the cost of all heights. Yeah. Because when you build, you need to work, all the way up, right? Remember, we use the bottom up. When we build a heap, we do the local heapify operation starting from the bottom level, bottom up. Then each level we work on local triangle, right? From right to left. Yeah, following that order, level by level. Okay? Yeah. Here we need to repeat that building process. Yeah. All right. Cost of max heapify for all nodes of height h. Let's just look at the height h. Height h. Work. How much work do we need to do for just one node at height h? Okay? We only want to look at one node at height h. Okay? One. Because we know the total number of nodes, right? So we only do one, then we do multiplication. For each node, we need to do this much work. We have total this many nodes, we do multiplication. Okay? So we only need to look at one typical node of height h. Yeah. How much work we need to do? Local heapify. Yeah. We need to recall this local heapify operation. Okay? All right. This number is the upper bound of that number, right? So this time we use this upper bound. Okay? We do not use the exact counting number. Yeah. Although we can use that because the upper bound is simpler, right? Yeah. Upper bound is simpler, just slightly more than that exact number. Yeah. But one difference, why is so important, right? That one difference is not a big deal. Yeah. All right. So, all right. Yeah. And for each height h, we need to do this much work. Can you see that? Some constant multiple times h. Yeah, here, let me draw a diagram. Yeah. Draw a diagram, height h. Yeah, all right. All right. Suppose this node, height h node. Yeah. Height h. Height h means from this node, it needs to go through total how many edges to reach a leaf. We start from this node, then we go down, we follow a path. Okay? You follow a path, but your destination is one of the leaf nodes. Yeah. All right, that path you need to go through h edges to reach the bottom, h edges. Yeah. And here we use the longest path, okay? Here, we use the longest path. Longest path for the worst case, right? Longest path. Because we want to do it for the worst case. Yeah, worst case. Because some paths shorter, right? Yeah, because one level higher, a little higher, so, shorter. Yeah, but we will take the longest path for the worst case, okay? Each edge, you only need to do one operation, one swap operation, right? Each edge, okay? Edge. Each edges, you do at the most H swap operations, right? That's why the total cost is this big O of H. How about that? The total cost is big O of H. Yeah, all right. Then you multiply these numbers. So for level H, height H work, to do local heapify for all the nodes at height H, you need to multiply these two numbers together. Okay, all right, yeah, heights. But you need to go through from 1 to floor function of log base 2. Yeah, because that's the maximum number you can have, right? The height. Because leaf level 0, you come from 0, okay? Then your largest number is the floor function of that. Okay, all right, yeah. Then, we skip the leaves. Leaves, we do not need to fix anything, right? Local heapify, nothing to do at the leaf level. Yeah. All right, then our summation, because we need to accumulate all the local heapify cost for all the internal nodes. Yeah, no external nodes, all internal nodes. So this is the summation. Summation. All right, yeah. Okay, all right. The next question, how to estimate the summation mathematically, okay? This big O of H, we can replace by C constant times H. C constant, we can take it out of the summation. Yeah, C constant, certain C constant, okay? Yeah, all right, yeah. Yeah, so then, because ceiling function, can we make this, because we want to remove ceiling function, right? Ceiling function in math calculation, not easy to handle, right? So we want to eliminate ceiling function. To eliminate, we enlarge it. With +1, it is larger than the ceiling function, right? Yeah, +1, yeah. So we are generous here. We are very generous here, yeah. So we're plus, yeah. All right. Then, so you have two summations because you have +1, okay? Yeah. The +1, the second summation is corresponding to the +1. The first summation, so that part, yeah. So we calculate these two, yeah. All right. But the second one is easy to calculate, right? Second summation, easy to calculate. We plug in the formula, the second summation, yeah. Yeah. So 1/2 times log base 2 times log base 2 of 1. Yeah. That's easy, yeah. But that is, we use big O notation, that big O of log base 2 of n squared. But it's log base 2 of n. Log base 2, we know, comparing with m, much smaller, right? Yeah. So this term, we do not worry about it. This term, that term, pretty small, okay? Yeah, that term, minor term, we can even ignore it. Yeah. Because comparing with n, too small, yeah, too small. So we are fine with the second summation, but we worry about the first sum. Is the first summation too big? Yeah, so that's our concern. The first summation, we don't want to see a big expression number. Yeah. All right, let's do the first summation. Okay, all right. Estimate the main term. This is the main term. Yeah, we need to estimate. Yeah, all right. Yeah. All right. All right. Yeah. That n, because when we do summation, yeah, here, our focus is on this summation. Yeah. This big O, we can use C constant to replace it. Yeah, yeah. All right. So the C constant, we can take it up to the front. Yeah. Then, when we do the summation, can we treat that n as constant? Because n never change. When we do the summation, do the addition, okay? Yeah, term by term, that n number it never changes. If n number never changes, can we treat it as a constant and take it out of the summation? Yeah. Yes. This h is a variable. N is a constant. Okay? H is a variable. N is constant, never changes during the summation operation. Yeah, no change. That's why we treat it as a constant. We take it out of the summation. All right. Then we only work the part inside the summation. Okay. All right. When we work, yeah. Do you feel this, upper limit for the summation operation? Upper limit, log of base 2 seeding function. Do you feel, a little complicated to work on, right? Yeah, so that it's not a nice expression, right? Complicated to work on. Yeah. The question, how do we simplify it? Yeah. Because, for a complex expression, so usually it means complicated work. Okay? So we want to do it as simple as possible in the simplest way. So we want to simplify the expression first. And we want to eliminate some complex expression. If we can do it, we want to eliminate it. Yeah. Here, how to get rid of it. Okay? How to get rid of it? Summation. Yeah. Yeah. So our goal, we estimate the total number for this summation thing. Okay? All right. Now, when we do the estimation, we need to do the simplification frequently, right? We do the simplification frequently. When you do simplification, you want the expression simpler, right? Yeah. You want the expression simpler. But you want to still control the whole summation, right? You put the whole summation under your control. And you do not want to break your logic. Yeah. Because when you do the estimate, there is a logic behind it. You don't want to break that logic. So you want to preserve the logic. But under that logic principle there, you want to do the simplification. That's the general way we do the simplification. Yeah. All right. So in your simplification, can you transform the summation formula, replace it with a larger expression or a smaller expression? Yeah. Because when you do the transformation, your goal is the simplification is your goal. Okay? Yeah. Under that goal, you can modify the value slightly, right? Yeah. Modifying the value slightly, make the expression simpler. That's your goal. Okay? Simpler. Simpler is better. Yeah. But when you modify the value, based on the logic, is it okay to make that value slightly larger, or is it okay to make that value slightly smaller? So which direction is okay? One direction is okay, but the other direction is not that okay. Yeah. When you replace it by a larger number, it's okay. From the logic point of view, it's okay. Why? Because if you can control the larger number, can you control the previous smaller number? Right? If you have a good control on the larger replacement number, then it means you have even better control on the previous smaller number, right? But if you replace it by a smaller number, even if you have a control on a smaller number, you may not have a good control on the original number that is larger than that, right? Yeah. So here, it's okay, we can make the number larger, but it's not okay to make that number smaller. Yeah. The larger, we hope we can still control that larger expression. Okay? Based on that logic. That's the logic. Okay? Based on that logic, here we want to make it slightly larger, but still under our control. All right. Make it larger. Can we replace this expression by larger expression? Yeah, by larger. Then we make the whole summation larger. Yeah. Here we are very generous when we do the enlargement here. We do it very generous. We make it infinity. How about that? So generous. Okay? Yeah. We add all the remaining terms. So this series. So we add up all possible such terms to infinity. We want to see if we can control this summation. The summation of this infinite series. If we can control that, can we go back to say we can do better control on the original summation? Yeah, that's the logic. Okay, all right. Next, we need to work on the infinite series. And we want to see, can we control it? Okay? Yeah, all right. Yeah. And here we treat working on the infinite series, it's better than on the finite series, right? Finite series, we need to deal with the log base 2 of that. That's too hard. Yeah. Okay? But infinite series, the biggest benefit here, we never need to worry about the log base 2 of it. Yeah. We get rid of log base 2 of it, right? Yeah. All right. This is the summation infinite series. Look at this. The question, how to calculate the summation? Yeah. Let me check how much time I have. Yeah, I want to, complete the whole topic today. Yeah. So we have enough time. Yeah. Yeah. All right. Less than 10 minutes, I think. But 5 minutes. Yeah. Yeah. All right. Let's do the calculate the summation. Yeah. Here, calculate summation, there is a trick, small technique we need to use. Okay, all right. S equals that. Yeah. All right. Now let's double this series summation S. Double it. 2s. 2s. Okay. 2s. We get another series. Here you can see all the denominator power of 2. Yeah. Now you compare these two series. Yeah. And they have corresponding terms. The terms with the same denominator, okay? The third term with the same denominator, okay? One-to-one correspondence, yeah. The first term, left out, yeah. Yeah. All right. Then the question, if we do subtraction, the bottom one minus the top one, do subtraction, and do the subtraction in each circle. Inside each circle, see what do we get. Okay, all right. And all the way down, to the infinity. Okay, yeah. So you will get left hand side just the same S, right hand side this geometric series. Geometric series. 1/2 plus 1/4 power of 2 denominator. Numerator always 1. Numerator always 1, yeah, all the way down to infinity. The summation equals 1, right? Yeah. The formula to calculate this infinite series. Yeah. Use the first term, so that's 1/2, divided by over 1 minus the common ratio. Common ratio is 1/2, right? Yeah, common ratio of the geometry is 1/2. So based on this formula, it's 1. Okay? It is 1. That's the formula. Okay? All right? Yeah. So here, it's 1. Yeah. Then, S equals 1. Is it under control? Yeah. The infinite series, S is 1, under control. All right? If we go back to the log base 2 upper limit, it's less than 1, right? Yeah. Less than 1. Okay? That total summation is less than 1. Okay? So now our building building cost after our calculation, it is C times N, right? C times N. N factor out. Then the summation just the 1, C times N. Then it is bigger of N. Then our building cost, because that's the first summation. The second summation, log of base 2 of N squared, much smaller than N, right? Because log of base 2, we know, compare it with N, much, much smaller. Yeah. So that could be ignored, right? Yeah. So this part can be ignored. Okay? Yeah. So big O of N, at the beginning of our discussion, we have 3 cases. Big O of N squared, N log N, N. If the building cost is big O of N, then we feel very comfortable, right? Yeah. See, you know. So we are willing to spend this much cost, big O of N, to build a heap. Then we run the max heap. Okay? We run the max heap. All right. Let me see how much time. Yeah. 42. Oh. All right. 42. Yeah. So let me leave it to next time. Next time we complete the heap sort. Yeah. The last step, heap sort. Because now we have a max heap, okay, ready for the heap sort. Yeah. So last time I planned to do the heap sort. After that, I will do another important question related to our homework assignment. Oh, don't forget to do one thing next time. Because this week, before your deadline, this is the next class, is the last class before the deadline, right? So you have a chance to ask me homework questions, okay? After I complete my topic, you can ask me, you know, any homework question if you want a hint. If you want hints, bring up your questions. If you do not ask me, then I do not talk about it, okay? So I treat you can do everything, okay? So if you need some information from me, don't forget to bring it up next time, okay? The last chance before the deadline, yeah. All right, that's it.